Hello friends, welcome to MEP Junction. Today I will be sharing the first video of HVAC chill water system, and in this presentation we'll learn how constant primary system work in commercial building and industry for HVAC application. What would be the overall plant efficiency with this system and its advantages and drawbacks. If you are new to the channel, please like and subscribe for more such informative videos. So let us start the video. We'll first understand the types of chill water system in the HVAC. The first one is the constant primary system, where there is a fixed speed chillers and the fixed speed pumps. Then the constant primary and the variable secondary system, where fixed speed chillers, fixed speed primary pump, but there is a secondary pump system also, which is a variable one. Then there is a variable primary, variable secondary, where chillers and the pumps all are variable. Then the variable primary flow system, where again the chillers and pumps are variable. Let us have a deep dive in constant primary chill water system. The constant primary system is the simplest chilled water distribution scheme and looks like this schematic. This requires fixed speed cooling towers and then the fixed speed chillers, a fixed speed condenser water pumps, a fixed speed primary pumps, which is a chill water circulator pumps, then three-way valves, AHU air handling units. The air handling units are used to control and maintain the indoor air temperature, humidity, quality, and the comfort. Here we will understand how chilled water being circulated through this AHU and warm air entering the AHUs and pass over the coils to transfer the heat to the cold chilled water to have the cooling in the air, right? The space. There is two sections in this. One is the condenser water side and second is the evaporator side, chill water side. Let us understand one by one. In the condenser side, water keeps circulating in a fixed volume through the chillers with the help of this condenser water pump. Now, in this circuit, you see a pressure break here at the cooling tower, and that's the reason this circuit is called as an open loop circuit, as there is a pressure break at this point because water is coming at this point and the cooling tower nozzle is going to be spray the water into the cooling tower and it is going to be collected at the basin. The pumps here are designed to take care of the head loss across the pipeline, this complete pipeline, and the head loss across various valves and the fittings, the chiller condenser coils, and the cooling tower nozzles. On the flow, how to calculate the flow for these pumps? So required flow data is to be provided by the chiller manufacturer, or you can consider a 2.5 to 3 GPM per ton of cooling capacity as a thumb rule to get the condenser water flow. The common range for the condenser side delta T may vary between 5 degree to 10 degrees Celsius. This is based on the Indian climate conditions. Since this is an open loop, the pump selection is very important here, and with the right NPSHR, if pump is being selected, then we can avoid the cavitation into the condenser water pumps. The best way to avoid the cavitation is if we can able to maintain a height of 15-meter plus for the cooling tower, between the cooling tower and the pump, then we can easily avoid the cavitation, as most of the manufacturer can easily provide you the pump either horizontal or the vertical centrifugal pumps within a limit of 5-meter NPSHR. Now we'll go to the next. In the evaporator side, water keeps circulating in a fixed volume through the chillers and AHU air handling units with the help of these primary chill water pumps. This circuit is called as a closed loop circulation circuit, as there is no pressure break. As you can see, from the outlet of the pump, water is circulating through the chillers and through the AHUs and again coming back through the return line into the pumps. These pumps are designed to take care of the head loss across the pipelines. the various valves and the fittings, pressure loss across the chiller evaporator coil and the AHU cooling coil. The required flow data is to be provided by the chiller manufacturer for designing of these pumps, or you may consider 2 to 2.5 US GPM per ton of cooling capacity as a thumb rule to get the evaporator water flow. On the delta T, the common delta T, the temperature difference across the chiller is considered as 5 degrees Celsius, and this is designed to have 12 degree Celsius as an inlet to the chiller and 7 degrees Celsius outlet from the chiller. This is typical for as per the India climate condition, and there is three different operations is shown in the three-way valve. We will discuss one by one. In the first three-way valve operation, you can see the water is flowing from the supply line, chill water line, to the AHU, and the bypass line is having no flow at this time. It means this AHU is at 100% load right now, right? And we can understand like this: the 7 degree temperature coming in, and in the return it is coming 12 degree to have the delta T of 5 degree. The next, you can see all three are green. It means the water is going through the AHUs as well as through the bypass line. It means this AHU is partial loaded, and maybe if I consider 50-50%, the 50% coming from the bypass and 50% consider from the AHU side. So the inlet again here is 7 degrees Celsius, but the outlet may not be 12 degree. It may be 9 degree. It may be 10 degrees Celsius. So this is a example of a partial load condition here. And the third is if there is no load. In case of no load condition, you can see the all the chill water is going to be bypassed and there is no flow through the AHU cooling coil. So these are the typical three conditions which can be seen into the constant primary systems. If we combine both the circuits together, you can see a constant primary system ready with this complete schematic, right? I hope you have now understanding that how the condenser side of the system or the circuit is working and how the evaporator side circuit is working, and combining both is the constant primary system. In case of any queries, please put your question in the comments. I'll try to revert as soon as possible. To understand the chiller plant efficiency for the constant primary system, let us first understand the scale for different kind of chilled water systems. This divide into the four different categories. One is the poor, then fair, good, and excellent. These four scales are divided based on the type of plants. Like the first is the legacy plant. The legacy plants are those plant which is typically plus 15 years and the old plant where there is no VFD and plants are running on the fixed speed. And the IKW per TR fall between 1 to plus 1.2 IKW per TR. Sometime I have witnessed it reached up to 1.6, 1.7 IKW per TR, which is very high, and the plant efficiency is very, very low. Then there is a fair which comes in the conventional plant, and the conventional plant is those plant where few equipment is having VFD and few equipments are running in the fixed speed, and it falls from 0.8 to 1 IKW per TR. And then there is an efficient plant which is comes under a good category, and efficient plants are those plants where we witness all the equipment is having VFD and chilled water system chiller plant is going to be operated in 100% automation. When I say 100% automation, it means there is no single manual interference to operate the plant. Then there is high efficiency plant. When you go with the new age technology for the chillers, for the pumps and efficient system, then you will get the chiller plant efficiency between around 0.55 to 0.7 IKW per TR, which comes into excellent category. And the ultra high efficient plant, when you go with the a very advanced chiller like magnetic bearing chiller and all, then you will also able to get this range of IKW per TR, which is 0.4 to 0.5, which is a very high efficient plant. For constant primary system, this is the reason where it falls. So it gives around 1 to plus 1.2 IKW per TR, which is on the higher side, and that's the reason the efficiency of these plants are very low. So let us discuss the advantages and the drawbacks of having constant primary systems. The first one is simplest pump configuration. So either it is condenser water pump, it's fixed speed, and then the primary chill water pump is also fixed speed. Very simple configuration. Then low installation cost. There is no VFD on pumps or on the chiller or on the cooling tower. One set of pumps, so there is only primary pumps. There is no secondary pumps. Much simpler control and operation. So there is no any kind of PLC or the controller which is required to control the pumps. So it's on off operation. So it's very simple. On the drawback side, the first and the very important is the low delta T syndrome. And this is the reason why the chiller plant efficiency is very low in this case. So what is the low delta T syndrome? If the actual delta T of the chiller plant is coming less than the design delta T of the chiller, which is 5 degrees Celsius in our case, then this condition is called as a low delta T syndrome. It caused due to lowering the return water temperature due to insufficient heat transfer, low load conditions as we discussed, right? Fixed speed systems which cause water to circulate even when there is no requirement of the chill water in the low side or in the AHU, right? Or some other cause also there, like if the heat exchanger, the AHUs are not designed properly, it is over designed, right? There is some manual bypass is open into the system, right? So there is many important aspects into it which creates a low delta T syndrome in the constant primary system, or I would say in the pressure based chill water systems. We will discuss more on the low delta T point, this particular topic. I will make a specific presentation into it because it's very important topic to discuss further. The next is pump energy wasted. So as you can see, the pump is fixed speed and it has to work. Either there is a requirement on the AHU side or not. So the pump energy is wasted for the primary chill water system, as well as for the condenser side also. If we can have some saving by going with the variable condenser pump as well. The lower chiller plant efficiency, we already seen that on the plant efficiency scale, and high IKW per TR of the HVAC system we discussed. Poor control on the comfort cooling, right? So this is the another adverse impact. So we are going with the chill water system to have the comfort cooling, but because of this fixed speed operations, we have to compromise with the comfort cooling. So the poor control on the comfort cooling side is the another drawback which is very important to consider with the constant primary systems. With this, thank you so much for your time. If you enjoyed this video, please like, share and subscribe to get the latest notifications of my videos. Bye bye, take care.